Okay. I think you can hear me. So I think it's time to get started. Maybe folks are still coming to the classroom, but yeah, it's time to get started. So here's the today's plan. So I continue talking about this activity programming. And I hope that for today, you have a fair amount of time working on this notebook. And the way you work on this notebook is somewhat different from what used to be, how you used to be working on the notebook. So you have this collaborative Excel workbook. So each problem is actually not very difficult. So basically, it simply asks you to run the compiler and see what happens. So there's no complex programming exercise, but just doing this by yourself is somewhat boring. So I'm just trying to share what you have seen in this shared Excel workbook. So I get to this later when you start working on this, after I finish this part. Then I will continue talking about this assembly things, so somewhat more difficult part, and hope probably you don't have time to start working on this, but the next workbook is, Jupyter notebook is already released. So if you have finished everything, you can start working on it. So yeah, let's start talking about this. Okay, so from the last week, I started talking about this SIMD programming. It's a very important element to get performance on CPU. So by the SIMD is very CPU thing, not GPU. And I think, yeah, this is where we left off. But before getting into it, I just try to refresh your memories, and especially why I'm talking about this apparently very low-level thing. So yeah, SIMD is, like I said, yes, the last week, an instruction that operates on multiple data with a single instruction. And there are many ways you can actually use these SIMD instructions in your program. And in the first part, we will be mainly focused on so-called high-level SIMD programming. In high-level, in the sense that you actually do not manipulate SIMD values explicitly. So you just write ordinary loop. So it doesn't look any different from ordinary programs without using SIMD. And hope that the compiler will do the job for you. So in that sense, so in this high-level SIMD programming, you don't necessarily have to know much about SIMD programming. In theory, it's possible that you don't know anything about SIMD, but the compiler somehow is able to vectorize it. But this actually doesn't happen often. And especially because you are using high-level SIMD programming without explicitly saying anything about SIMD, it is actually important, often important for you to know that if the compiler was able to vectorize the code you were given, you gave to the compiler, and if so, how? So that's the reason why you at least need to know something about what SIMD instructions actually look like. So they're actually very similar instructions, but one is actually SIMD instructions and the others are not SIMD instructions. This difference is huge, and instruction names are very similar. So you want to know which instructions are actually SIMD instructions and which are not, to know whether the compiler was able to vectorize your code. So that's why I started with this. Okay, so all the instructions I just wrote here are all multiplying instructions. But there are so many varieties. And actually, when you look at these instruction names, the last two characters are very important, like I said the last week. So this SS means, the second last character means whether it is scalar instruction or SIMD instruction. So if it is S, it means a scalar instruction working on a single value. If it is P, it is SIMD instruction. So it actually stands for packed instruction. So many values are packed. So that's why it's so named. So the distinction between something S and something P are huge, right? So P is a SIMD instruction. And the last character stands for the type of the value instructions we operate on. So S is a single precision, and D is a double precision. So there are actually other versions working on integers, but when it comes to floating point numbers, it is either S or D. So they look very similar, but what actually happens very different. So in the sense that how many operations are actually done with this single instruction. So these two instructions, SS and SD, it takes only one operand, one pair of operand. So you are multiplying two values, so a pair of operand. So there are so many SIMD instructions. Well, actually, even the instruction names are exactly the same. But the difference is the kind of registers you are taking as operands. So there are three versions, X, Y, and Z. Like I said in the last week, so X registers are 128 bits, this one. And YMM registers are 256 bits. And finally, ZMM is 512 bits. So even though instruction names are exactly the same, depending on what kind of registers they are taking as operands, the number of operands they are actually operating on are different, right? So because this is 128 bits, so if it is single precision numbers, it is 4 single precision numbers. So in this case, it is operating on 4 single precision numbers. So this way you reason about what compilers are exactly doing. So you don't have to know all the details about the instruction generated by the compiler, but use these knowledge to know whether the compiler was able to vectorize it or not. So this is basically what you need to know about SIMD instructions for now. So you get some vague knowledge about what kind of instructions are available. So I got a question. So the question was, are there 3 sets of different registers, or does it smartly assign all based on size to the same set of registers? Yeah, so this is exactly what I talked about in the earlier slide, this one. So actually, the last 256 bits of this DMM registers, actually the areas of YMM registers with the same number. So physically, for example, the CPU supporting this DMM registers only have DMM registers, but the part of them can be used either YMM registers or XMM registers. Does that answer to your question? So if you use only XMM on GMM, GPU, I think CPU, there are lots of ways. Yes, yes. So there are even programs that do not use SIMD instructions at all. So they are in a way waste in terms of the performance. Okay. So this is some the minimum knowledge about what SIMD instructions look like, and there are so many variety of SIMD instructions doing addition, subtractions, memory access, these things. So given that knowledge, you can obviously understand that SIMD will be very good at parallelizing, so vectorizing computations, doing almost exactly the same series of instructions on contiguous data. So it is basically good at vectorizing this kind of for loops, accelerating this kind of for loops. So each iteration executes S for a single value of y, right? So this is the template of any for loop, right? So SIMD or vectorization is essentially converting this loop into something like this. So you basically execute L consecutive iterations at the same time using SIMD instructions. So S may be a very complex statement or even a series of statements, but the way you vectorize this computation is, so you basically look at every single statement in S and every single expression in S and somehow replace originally scalar instructions into corresponding vector instructions. So this is, well, at least conceptually, how you vectorize arbitrary for statements. So for reasons that become clear later, so it is very difficult to vectorize this for loop. If, for example, S has a very complex control flow, so depending on which iterations you are executing, or one iteration does something A, and the next iteration does completely different things. So it is not good at vectorizing this kind of computation. And likewise, as it becomes clear later, it is not good at vectorizing for loops that iterate on non-contiguous data. So two consecutive iterations like to work on consecutive elements of an array. So this is what the SIMD is very good at. So you see this through the experiments in the Jupyter notebook. So there are actually, like I said, many ways to use SIMD instructions. So you necessarily do not have to know too much about SIMD instructions. So the simplest is something called auto-vectorization. So you simply write ordinary loops, and the compiler does everything else. And it doesn't succeed very often. And there are some language extensions or directives to explicitly instruct the compiler to use SIMD for this for loop, for example. So in fact, OpenMP already has a SIMD directive. So just like you parallelize a particular for loop by inserting pragma OMP parallel for or something like that, you can say pragma OMP SIMD or something like that, just to instruct the compiler to try to use SIMD instructions for a particular for loop. So I get into this later, and you'll see how this works in the Jupyter notebook. And then there are some other things like something called array languages. So you write an expression that represents the whole array. And rather than you iterate through each element of the array, you simply say, okay, add the entire elements of this array with the entire element of another array, and the compiler vectorizes this computation. So there are some several ways along this approach. And if the first things are called sort of high-level SIMD programming, and the other three approaches, especially these two, are something called the low-level SIMD programming. So I'll get into this in the later part of hopefully today's lecture. So first about high-level approach, so something called the auto-loop vectorization. So like I say, so in this approach, you simply write ordinary scalar loops and just hope the compiler does the job. So this is the simplest code for which almost any vectorizing compiler is able to handle. So just a simple for loop. The iteration j takes the j's value from the array x and x plus c and stores it into the same place. So with SIMD multiplication, SIMD addition, and SIMD load and store instructions that takes the address of the first element and get the consecutive whatever number of elements that are supported by the CPU. You can easily imagine that this is very amenable to vectorization, right? So you just compile this code but with just a few options that instruct the compiler to use these instructions. So so whether you actually need these options depend on time. So when the time evolves, and for example, this AVX 512F instructions are become very common, then chances are that you don't have to say anything like this at all. But for the time being, you need to explicitly say, I want to use these instructions, AVX 512F and FMA, fuse multiplier instructions. And this -03 is the optimization option. So that increases the optimization level, so that the compiler should work hard to vectorize it. So for details, you can simply follow the notebook instructions in the notebook. And there are other options that tell you whether the compiler was able to vectorize it or not. So without this information, it is very difficult to know if the code you are executing is actually vectorized or not. So the details again in the Jupyter notebook. But so these options are very important when you try to vectorize your code. With that said, these are not the only thing you want to look into. So the compiler options are not, sorry. So the message from the compilers are not the only thing you want to look into. So don't hesitate to look into the assembly code generated by the compiler. For that, you simply give -s option to the compiler. Oops. I think it's all right. Okay. So so give -s option to the compiler, and the compiler generates the assembly code as a separate as an output. So you just look into the assembly code, but it is often very difficult to locate the assembly code that corresponds to the loop you are interested in. So for that, but there's interesting trick you can play with. So you just insert something called the inline assembly code, and these comments are just inserted into the generated assembly. So actually the compiler doesn't have any idea about what this string does. So the compiler actually think it might be actual instructions. So it doesn't assume anything about what this piece of string does. So the compiler basically copies this string into the assembly code. So this helps you locate the code generated for this particular for loop. So this is again in the Jupyter notebook. And this is automatic vectorization. And somewhat more explicit is something called SIMD directives in OpenMP. So in OpenMP, you have a SIMD pragma, so which is a directive to the compiler to instruct the compiler to vectorize the following for loop. And actually, there's a similar syntax restriction that apply to the OMP for loop. So it only takes for loop for which the iteration space can be easily recognized and identified at the beginning of the for loop. So the kind of for loop to which this SIMD pragma can apply is pretty much the same as the kind of loop for which OMP4 can apply. And the other thing is something called the declare SIMD pragma. So it is the pragma that instruct the compiler to generate a vectorized version of a particular function. So it is attached just in front of a function definition or declaration. So without this declare SIMD thing, whenever a loop contains a function call typically does not have any vectorized version. So the compiler quickly needs to resort to Scala code. So it easily gives up the vectorizing the code when a function call is included. But with this declare SIMD, there's a SIMD, so vectorized version of the function, and the compiler somehow knows it. So the compiler may be able to vectorize loop containing function calls. So this is what the OMP SIMD pragma looks like. So just like OMP4, you simply say OMP SIMD just in front of for loop. And there are some hints to the compiler specifying how each of these, also how some of the variables in this statement change over iterations. Like, for example, uniform basically says this variable does not change across iterations. And linear says these variables increment by this stride you specify here across from one iteration to next. For example, if you say linear x colon 1, then it tells the compiler that x will be incremented every single iteration by 1. So this helps compiler vectorize a particular loop. So here's simple example using this OMP's SIMD. So for this particular loop, you don't have to say anything like that. So just auto vectorization will succeed. But at times, the compiler cannot figure out whether it is safe to vectorize a particular loop. So if you give this OMP SIMD, chances are that even in such cases, the loop can be vectorized. Basically, the effect of this OMP SIMD is, okay, so you guarantee that it is safe to vectorize this for loop. In other words, it is safe to execute several iterations at the same time rather than one after another. So unless the compiler is able to prove that this is indeed the case, auto-vectorization will fail. But with OMP SIMD, in a way, it is up to you who guarantees that it is safe to do so. Okay, so this is a declare SIMD thing. So you give this declare SIMD directive in front of function definition or declaration. So it is an instruction to the compiler. Okay, so saying, so you need to generate a vectorized version of this function. So you can check details in the Jupyter notebook. And this can also be used to tell the compiler there is a vectorized version available elsewhere, so compiled elsewhere. So loops containing function calls to this function can still be vectorized. You just call the vectorized version of the particular function. So there are so many ways, so many reasons that vectorization fails. And actually, you simply write an arbitrary loop, chances are that it almost certainly fails. So only for loop that you carefully write so that vectorization will succeed can be vectorized in practice. So you'll see this in the Jupyter notebook. And just to list a few. One is something called aliasing. If iterations are going to maybe accessing the same element and one of which is right, then it may not be safe to execute multiple iterations at the same time. So unless the compiler is absolutely sure that this doesn't happen, then auto-vectorization at least fails. So OMP SIMD pragma is one way to circumvent this situation, but still other situations that even OMP SIMD will fail. And in general, if there is a complex control flow inside the loop iteration, then compiler tends to give up the vectorization. Well, so you'll see that how easily the compiler will fail to vectorize just because there's, for example, if a statement or another loop inside a loop. And the other reason is loops accessing arrays non-contiguously. So you see this in the notebook. So this slide goes into each of them in some more details. But well, rather than listening to my talking for another 20 or 30 minutes, let's have a time to work on this Jupyter notebook. So the Jupyter notebook you'll be working on is this PD05. And like I wrote in the lecture homepage, so your observation, what you see by running a compiler for a particular piece of code will be shared in this Jupyter notebook. So everybody should make sure that you are able to access this workbook, Excel. And you first should visit this README Excel and find your name. And the next to your name is the workbook you should be working in. So, for example, if you just open this notebook, and so just write your name in the first empty row, and get the column name here. For example, if you write your name here, then the column you should write your answer to is this J column. And just go to the next sheet. And for example, if you are supposed to work in this J column, then yeah, write your username again here and write your observation here. And I guess you need to just shrink it a little bit. So for each of the piece of code I gave in the Jupyter notebook, for example, where is it? Okay, so if you open this notebook from this section 8, yes, it is section 8. So you are going to learn, so when vectorization succeeds or fails. So you are given many small pieces of code, and you are asked to run the compiler and generate the assembly code. And you are actually supposed to observe what the compiler says in the message. So whether the compiler was able to successfully vectorize it or not. And you are also asked to look into the assembly code, the generated assembly code. For example, run this compiler here. Sorry. So I need to set the path as always. And then, so run the compiler and look at the message that the compiler emits. So loop not vectorized. So this particular compiler was not able to vectorize the code given here. And yeah, think about why. And you are also asked to look into the assembly code. Where was it? Where's the code that I just compiled? Is this? Okay, so in this particular program, I didn't somehow ask to look into the assembly code. So let me do this. And okay, so by running this code, you can actually look into the assembly that is generated and try to locate what is the assembly code that corresponds to this loop. And you typically find a innermost loop. So the compiler actually does so many things to make this loop run faster. But often there's a smallest innermost loop in this particular case, this one. So this instruction jumps to this label. And essentially, this is the instruction sequences in which the most time will be spent. So try to locate this piece of innermost loop in the assembly and paste it into the Excel sheet in this column. And in this column, you paste the compiler message that tells you if it was able to vectorize it or not. And you can also write some other remarks. So detailed instructions are actually so the README file. So maybe you wanna spend a few minutes reading through this. So I guess it's time to get started working on this. So let's have this time until something like 20 minutes, something like until 5:45. And also, so the other thing is, so so designated each of you to a particular notebook just for the purpose of load balancing. But for example, if you want to work with your friend next to you, especially in the classroom, you are allowed to do so. So if you want to work on the same workbook with your friend, just change the workbook you work on. So either case, please copy the link to the actual workbook you will be working on in this column. For example, if you somehow decide to work on workbook 05, then you simply copy this link to workbook 05 next to your name. So get started this way. So even if you do not change the workbook you want to work on, please make sure that you copy the link to the workbook right before you start working on it, so that I can have some ideas about how many people are actually working. And which workbook. Okay, so I got a question. So you cannot open the Excel sheet. So do you want to show your browser? So let me see what exactly happens if you don't mind. So Karina, do you wanna show your browser? Okay. So I stopped the screen sharing. So now you can start screen sharing. All right. So okay. So is it French? Okay. So what does it say? So so can you give me the English translation? Or does it actually say something like it cannot connect to the service or something like that? Okay. Maybe one thing you wanna try is to open the private window. Do you know how? Sure. Yes. 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 Copy the link. Oh, no, no, no. So you should write your Utoki account. So 10 digit. Oh, no, no. So you should add everything. Yes, Utoki. Hmm? What does it say? Okay, so no problem. Mm. So yes, yeah, at this point, yeah, of course you can dig into it, but I think it's better to dig into it later. So for now, not being able to write to the notebook isn't a big deal. So just work on the notebook. Does that sound okay for you? Okay, okay. So let's try to fix it later. Maybe you can just try later. I don't know, but somehow works. So there was a comment. Maybe you didn't have two-factor authentication activated. I don't think it matters. So Microsoft at this point doesn't need two-factor authentication. So in generally speaking, so Microsoft tends to be very easily screwed up somehow. So there's so many signing issues around Microsoft. So Google seems much better. And well, most of the time, if you open a private window, yeah, things just work fine. And so I got a question. Yeah, so this message is emitted by perhaps GCC, and it is somehow complaining about this particular. Oops, I forgot to start screen sharing. But remote folks can see the chat message actually. So yeah, actually the people in the classroom can see this. Okay, so there was no issue. But anyway, so yeah, so there was some strange message. Very difficult to interpret. Upon this statement, this is presumably emitted by the GCC as far as I remember. So that the question was that does this mean that even using explicit commands for checking if it is vectorized can affect the vectorization? Not very sure. I actually don't know what the GCC is exactly complaining about. But my understanding is, well, GCC somehow doesn't know, well, the GCC doesn't know what this particular assembly statement is doing. So, but it somehow, yeah, tries to vectorize this particular statement anyways, and say it fails to do so. So if you look at the assembly code generated by GCC, you can actually observe that the main loop you want to vectorize is indeed vectorized. So, well, honestly, for this particular compiler message, I don't know how you interpret it. So the loop itself seems vectorized. Okay. Okay, so let's get back to the talk. So yeah, I don't expect you guys to finish all of this, of course. So you're still working on it, but on the other hand, we don't want to use the whole class time just doing this. So you get some ideas, right? So let's resume speaking about the subject a little bit. So basically, the thing I want you guys to learn through this experiment is the whether vectorization succeeds or not. Well, it's very subtle, and it doesn't succeed as much as you hope. But this is the thing I want you guys to take away. So for example, the one loop that doesn't succeed, at least for auto vectorization, is a loop that looks like this. So just observe that this xi element is taken and the result gets written into the next element. So for example, when you run this loop or sequentially, then what happens is something like this, right? So you calculate something based on x0 and put the result into x1, which is then worked on in the next iteration, right? So these iterations depend on each other, right? So it's obviously not safe to vectorize it. So if the vectorization means that, okay, so you take the first, for example, 16 elements and do this calculation using SIMD instructions and get the result back into 16 elements at the same time. So this is obviously not the same as what this sequential loop tells you to do, right? So this is obviously a kind of loop that the compiler cannot automatically vectorize. So when the compiler tries to automatically vectorize, what it is trying to do is to preserve the original semantics in which the whole loop runs sequentially, right? And so in this kind of situation, if somehow you don't care about but the difference between this vectorized version and the original SIMD version, serial version, then you can say, okay, OMP SIMD, just to tell the compiler. You don't have to worry about it. So this is the result I actually want, right? So in this way, you can explicitly vectorize even this kind of, so even this kind of code. Yeah, another somewhat more interesting case is a loop that looks like this. So this looks very similar to the previous one, except that the left-hand side now becomes yi. So this loop looks safe to vectorize, but it is only so when x and y are indeed different arrays. So actually, there's a possibility that a y, for example, I is actually the same location as xi plus 1, in which case this loop actually does exactly the same thing as this one, right? So this loop, well, from humans' eyes, it looks safe to vectorize, but strictly speaking, it is not. So the way the compiler handles this loop is actually interesting. So somehow the client says that the loop was vectorized. And the message from GCC is somewhat more informative. So if you compare this loop with GCC, it says, okay, so loop version. So it basically says it generates two versions. So in one case, X and Y point to some different parts of the same array, whereas in the other version, X and Y pointing to different arrays, so it's safe to vectorize. So the compiler, in a way, is doing a very good job at vectorizing this kind of loop. So I don't want to get into each of them. But this is the kind of thing I want you to learn through this notebook. And the slide actually go through each and every reason why the compiler may fail to vectorize. For example, if there is a if statement like this, or if there is another for loop inside the loop you want to vectorize. So actually, there's no fundamental reason why the compiler is never able to vectorize this loop. And you can do so actually manually. It's not that the CPU doesn't have instructions to help vectorize this kind of loop, but somehow the compiler is generally very behind compared to what CPU actually has. So it's particularly frustrating that the compiler is not able to vectorize if the loop body has another loop inside. Well, generally speaking, it is reasonable because in general, you don't know how many times each of these iterates. So if the number of iterations depends on the value of I, then it's pretty complicated to vectorize, right? So depending on which length of the SIMD value you are talking about, the number of iterations is different. So in general, it is understandable that the compiler has difficult time vectorizing this kind of code, but it's not that it is impossible. And if, for example, if the loop has a function call, then there may be something else. And if a loop accesses arrays, for example, in this way, non-contiguous access. So the iteration 0 accesses x0. The next iteration accesses x2 rather than x1. So 0, 2, 4, 6. This kind of loop is already somewhat tricky to vectorize. Again, it's not that the CPU doesn't have instructions for doing this. Well, actually, recent Intel CPUs have something called the gather instructions. So you can actually manually vectorize this kind of code, but it's pretty much the case that the compiler is not able to vectorize this code for you. So this kind of thing you will be going through in the Jupyter Notebook PD05. So here's the summary and takeaways about the high-level vectorization. High-level vectorization meaning that you don't explicitly deal with vector values in your program. You just write a loop and let the compiler do the job. So basically, CPUs actually have necessary tools and instructions. But generally speaking, the compiler is behind CPUs. So whether the compiler is able to use all these tools provided by CPUs is another story. And when you feed the compiler with a loop, chances are that the compiler is not able to vectorize it, even if there's a way to vectorize it using all the instructions available to the CPU. So it is a part of the reason why you need to be familiar with assembly code generated by the compiler somewhat, and also master somewhat lower level programming for SIMDs. So which is exactly the next topic we will get into. So the next topic is something called the vector types. So what is vector types? So many compilers, including GCC, Clang, NVIDIA compilers, extend a C language by allowing you to define a type that explicitly represents a vector of values. So the main difference between what I have been talking about so far And what I will be talking about from now is, so from now on, you will be explicitly manipulating vector of values in your program. So the first thing you need to do is to define a data type that represents a vector of values. So this can be done in this way. So probably you may not be very familiar with this strange syntax, and it may be your first time you are exposed to this. So you say, okay, so this is defining a new type called float vector. It is basically float, single precision floating point numbers, except that it is a vector of floats, and the size is 64 bytes. So size being 64 bytes means it has 16 float values. But 64 bytes, in other words, it is 512 bits. So this definition is very suitable for CPU supporting 512 bit SIMD instructions, like Intel, the recent Intel machines. And so with that type defined, you can declare variables or expressions of this type. So X, Y, Z. So you can opt that each of these variables is allocated to assigned to a vector register, SIMD register. And one pleasing aspect of this extension is, so actually the compiler allows you to write ordinary arithmetic expressions like multiply and plus on these vector of values. And what happens is, so you are almost certain that for this particular multiplication, the compiler emits a vectorized SIMD instruction for multiplication. Because it is so explicit that you are doing, you are manipulating to vectors of values, right? So you don't have to write a loop at all. So you just write an ordinary arithmetic expression, and you are using vector of values. So in a way, it's very straightforward. And one more pleasing aspect is that all these compilers allow you to mix ordinary scalars and vectors just for your convenience. For example, you have ordinary scalar flow and a vector x and y. So when you write something like a multiplied by x, it is multiplying a scalar with a vector. But there's no instructions in the CPU who takes one scalar and one vector and multiply them. But you only have an instruction that takes two vectors. But this is a way that the compiler helps you write your program very conveniently. So essentially, the compiler emits an instruction that extends this scalar into a vector whose elements are all the same. So this is another pleasing aspect of this this feature. And you can, so there are some other things you cannot easily express with ordinary arithmetic expressions. For example, let's say you want to take a square root of a vector of values. If you simply write ordinary C function called square root, for example, x, square root of x, then the compiler complains. But square root is applicable only to a scalar floating point number or double precision floating point. So the scalar value. So there are things that you cannot do just by introducing a vector type and ordinary arithmetic expressions. In these cases, there are some functions specifically, for example, designed for taking the square root of 16 values. If there is a CPU instruction available that exactly does that. So these are generally called intrinsics. So I'll get to this later. So that's basically it. So you have a vector type that represents a vector of values, and you can manipulate them explicitly in your C program. And as far as you are doing only ordinary arithmetic expression, it looks pretty much the same as ordinary programs manipulating scalars. But for more complex things, you have functions called intrinsics. So that's pretty much it conceptually. Okay. So a small point, you don't necessarily have to remember all of this, but in reality, rather than this, you actually need to write something slightly more complex. So not just this vector size 64. You also need to say main alias and align size of plot. And the reason why you need to write this is, well, I don't want to get into it. So you just remember that this is a formula to introduce a vector type of any underlying type. Okay. So here's a small example using a vector extension. So let's say you want to vectorize this loop, right? So the same loop we discussed before. So by the way, so this code can be vectorized by any compiler. But let's say you want to do it manually. Then, so first you want to convert it into a pseudocode like this. So rather than, so you want to execute iteration from I to I plus L at the same time, right? So this is basically what the vectorization is all about. So you want to convert this loop into something like this. So the I is incremented L each time, right? And in a single iteration, you want to work on L iterations at the same time. L is the number of lanes in a single SIMD register. So for example, in the case of AVX 512, it's 16, if this is an array of floats, right? So you want to work on 16 iterations at the same time. So accordingly, you want to fetch 16 elements at the same time. So fetch is, expressed in this convenient formula. So fetch doesn't exist in the real C or C++, but you know what I mean, right? So you first write a pseudocode that looks like this, and you replace this into the real working C code. So in this particular case, the only thing you need to do is how to actually implement this vectorized load instruction, right? So rather than getting a single array element, you wanna get 16 consecutive elements from the array, right? So this can be done something like this. It's a slightly complicated, but basically, at the end of the day, you can write something as simple as this. So the trick is this V. So what V does is take the array element, LV, let's say, so Xi, take its address using this ampersand operator, and cast the pointer into the pointer to float V, and dereference it. So then, what happens is actually, okay, so you want to dereference a pointer to a vector of 16 floats, and the compiler emits a vectorized load instructions for this expression. So just by writing something like this, you vectorize this loop. So something as simple as this. The only thing okay, so in this slide, I assume that this L divides the number of iterations n. Well, if I doesn't if L doesn't divide n, for example, n is, let's say, 17, whereas L is 16, then you need to run some remainder iterations without using vector instructions. So how this is typically done is something like this. So you run vectorized iterations until as long as you have the full L elements left in the L iterations left, right? And after you get less than L iterations remaining, then you simply run the scalar loop. Yeah, manually doing so is very tedious, right? So you don't want to do that. So if your program allows you to make n a multiple of L, then you do so. Or just to avoid writing this remainder loops manually, remainder iterations manually. But at times it is unavoidable to write remainder iterations. So then you have to do it anyways. But just remember that there are some cases in which you need to do so. So, well, actually, there's not too much I have to talk about this vector type. But the only thing you need to master is how to convert an array of a collection of scalar values into a vector and vice versa. So you get some scalar arrays and how to make a vector of some elements in the array, or vice versa. So you get a vector of values and how to extract individual elements. Right. So once you are able to do this, you learn pretty much everything you need to learn. So in order to make a vector value, you typically do so from an array of scalars. So let's say you have a pointer to ordinary scalar floats. Then what you need to do is to simply get, for example, 16 consecutive elements of the array by, I'm sorry, so this should be float v multiply, rather than multiply float v. So take the address pointing to a float, single float, cast it into pointer to a vector of floats, and then dereference it, like I said before. So, and in order to avoid making your code so ugly, you want to define either a macro or a function, depending on whether you are familiar with C++ or only with C. So you can write convenient a function or macro like this, just like I explained in the last slide. So by having either macro or a function, you can write something like this. So whenever you have a variable or array element, also, but practically it should be an array element. So array element of a float scalar value, you just write a b of a scalar location. Then you get a vector starting from this element ai. 16 consecutive elements of the array. So this is typically the way you make a vector from an array of floats, and vice versa. So the thing is, so somehow you get a vector of values representing the collection of values. So how to get individual elements back? Well, you typically do so by storing the vector of values to an array of scalars. Well, just like before. So now left-hand side should be something like V of AI, and you simply assign a vector of values into this left-hand side. Then what happens is 16 values will be stored into 16 consecutive elements of this array A, starting from element I. And after this, you can get individual elements from this underlying array A. And as a matter of fact, actually, you can access a particular lane of a vector directly. So without going through another array of scalars, just like this. So you can directly get, for example, fourth element of this vector of floats, as if it is an array. But it is in fact not an array, but well, this is another language extension supported by the compiler. But one thing you might want to remember is that actually there's no CPU instruction that extracts a single element from a particular vector register or SIMD register, especially when this index is not known at compile time. So in general, you cannot do something like this very efficiently, especially when I is not known at compile time. So, but still, you can write something like this. But what actually happens in the assembly or machine code level is exactly like this. So there's an instruction that puts the entire 16 values into a memory and then get a particular element back. So it's not necessarily very efficient. So when you care about performance, you'd better not assume something like this is possible. Now, it is actually possible superficially, but what's happening underneath is might be very inefficient. Okay, so I got two questions. So one is, so when I write a cast operation like this one, and the question is it different from so-called reinterpret cast? I think there's no difference. I'm not very actually familiar with so many ways C++ allows you to cast one value from one type to another, but probably yes. So this traditional cast supported in C is equivalent to this something called a reinterpret cast. And the other question is there any boundary check for this vector? This access looks dangerous. So I don't know which one you are actually talking about. Is it this one? So yeah, there's no boundary check whatsoever. So yeah, it is indeed very dangerous. So yeah. So for example, what happens when I is larger than 16 or greater than or equal to 16? Yeah, you don't know what kind of value you end up getting. So the final element you're going to learn is something called vector intrinsics. So this covers something you cannot conveniently express using ordinary arithmetic expressions. So like I said before, let's say you wanna take a square root of 16 elements. There's a CPU instruction that supports it. But nevertheless, if you simply write square root of a value x, when x is a vector of floats, then the compiler complains. So intrinsics is a way to explicitly access all these available CPU instructions. So all these vector instructions supported by the CPU. So the way you want to use this on x86 processors you are playing with, you include this header x86 intrin.h. Then you get a set of available vector types. So just like I manually define, like float b. So these are already defined in different names in this header file. And you also get a lot of functions operating on these vector types. And you can check everything from this page. So just by following this link, and you get something. So the page, this page, intrinsics guide. So this lists all the available intrinsics. And yeah, there are so many functions, and names are very long and obscuring and yeah, somewhat scary. But if you can use whatever is necessary to vectorize your code, then you're going to be master of SIMD program. So like I said, the reason why this combination is so useful is that, so vectorizing a loop is largely about converting this original scalar loop into something like this. So what you need to do is to somehow craft the instruction sequences that execute L consecutive iterations at the same time, using SIMD instructions. So the combination of the vector types you have just learned and intrinsics gives you a very powerful way to manually vectorize code. So the manually vectorizing, meaning that you explicitly write statements or expressions that represents this, where statements executing L consecutive iterations at the same time, expressions having the values of L consecutive iterations in a single variable. So that is how you manually vectorize for loop. And so in practice, so when do you want to use this manual approach? Well, basically it's whenever your compiler fails. Well, it is actually happens very often. But generally speaking, the situation you particularly encounter often is a loop containing a branch, for which there's actually a CPU tools or instructions called predicated instructions and value blending instructions. And another situation is a loop accessing an array non-contiguously, as I said several times already, for which actually the CPU nowadays supports special load instructions, something called gather instructions and scatter instructions. And another a particularly important situation you want to manually vectorize is a loop containing another loop. Actually, this is very easy if all inner loops have the same trip count. So the number of iterations that inner loop iterates does not depend on the index value of the outer iterations. So, but even in this case, the compiler typically fails to vectorize the outer loop you want to vectorize. So this is particularly this is a situation manual vectorization is particularly useful and necessary. So let's talk about how to do this in general. But before getting into this is where some names you encounter when you do this intrinsic programming. So when you include this header file into your program, those are names that become available to your program. So for example, there is a set of vector types. So for example, __ M512, which represents 512-bit vector. And more specifically, it is 16 floats, floating point, single precision floating point numbers. So this __ M512D is well, so in terms of the physical registers, these do not make any difference. But in C program level, it is 8 double precision floating point numbers. And this is an integer. So this M512I is 8 long integers. So strangely, there are actually no 16 32-bit integers. But actually, there are instructions that can operate on this M512I as if it is a 16 integers. Well, that's very, in a way, confusing. So in terms of the type, there's no type representing 16 32-bit integers, even if there is actually an instruction that can operate on this as if it is 16 integers, so 32-bit integers. So similar types exist for 256 bits and 128 bits values, like M256, M256D, M256I, and yeah, M128, where M128D, M128I. And there are functions operating on these vector types, like, well, they are generally named like _MM512, blah, blah, blah. So this part represents what they actually do. So this is functions operating on 512-bit values. So there are also functions MM256 something. And interestingly, probably it's a historical reason, 128-bit versions are not named MM128. Or they are named just MM something. So each of these functions almost directly maps to a single assembly instruction. So actually, in this intrinsics too, there's a function that converts scalar values into a vector and vice, not vice versa. This is a function that takes a single scalar value. For example, in this case, single float number, 32-bit floating point number. single precision, and convert it into a 16, the same value, that F16 times. It is called somehow set 1 PS. And here's a slightly different version that takes 16 distinct values explicitly. So it takes 16 arguments and makes a vector of 16 floating point numbers. So this is exactly what I explained before in another way. It's essentially, yeah, it is exactly doing, yeah, something equivalent to this, but explicitly taking 16 different values as a function argument. Okay, so the one thing you might want to remember, and just let's take a slight look at this page, just to give you an idea about what kind of instructions are actually available. So for example, I already talked about, for example, there are so many multiply instructions, right? So if you search this page for example, mul PS, no, so okay, so mul PS. So it shows you so many variants of multiply instructions. And this PS still represents that it is a packed single precision version, right? So, and if you wanna look for example, 512-bit version, then you can just click here, so LX 512. So this restricts the search into 512 versions. Oops, apparently no. But still you see the M256. I don't know why. But anyway, so it narrows the search a little bit. So it becomes somewhat easier to find what you need. For example, by just looking at names, you may think this was exactly the instruction that takes two vector values and multiply them, right? So MM512 mul PS. So this corresponds to a vectorized multiplication instruction. So for example, if you wanna look for FMR, then you input FMA. And then there's so many different versions of FMA, but again, you are already restricting the search. Okay, so this further narrows the search space. And then, for example, you found FMR PD. This is a double precision 512-bit SIMD instructions for FMR. And you also find down here, okay, so now you're almost certain that there must be FMR PS, right? So then you find, okay, so FMR PS, right? And then you click here to know what it exactly does, to confirm that this is exactly what you want. So in this way, you want to work with this page, looking for the functions you want to use. So the last section of this slide is about how to actually manually vectorize loops. Compilers tend to fail to vectorize. So this is actually the in a way the most important part after going through this vector type and intrinsics. But this is exactly the reason why you wanna master vector types and intrinsics, right? So the first thing is So what if a loop contains branches? So like I said several times, and you will see in the Jupyter notebook that the compiler easily fails to vectorize a loop containing branches, or it's easily gives up vectorizing loops containing branches. So for this, CPUs actually have something called predicated instructions. So predicated instructions are SIMD instructions that, in addition to ordinary operands, take another vector of Boolean values, something called mask, that specifies length for which the instruction should be executed. The instruction takes effect. So for example, the ordinary instructions operate on all 16 values on the registers. For example, if each element is 4 bytes. But you can additionally specify a mask and say, okay, I will do this multiply and add instructions on this and this and this length only, and some other lengths are not affected. Yeah, this is something you can do with predicated instructions. So in C programming level, results on other lengths, so the lengths that are specified not to execute this instruction, are taken from another SIMD register, or sometimes simply set 0. So this is a contrast between ordinary SIMD instruction versus predicated versions. So this is non-predicated version. So ordinary add instruction that takes 2 vector values. So this ends up AI plus BI for each lane, right? But predicated version, so actually there are 2 predicated versions. One is something called mask Z, and the other is simply mask. And mask Z, on each lane that is specified to be executed using this mask variable. So if this the particular lane of this mask variable is set, then you should execute this additional instruction, and otherwise 0. And in this the last version, for lanes that are not that are specified not to execute, that the value is taken from another register C. So in this way, you can execute a particular instruction only on subset of lanes. So this is how you generally handle branches. So in then branch, you execute particular instructions only on lanes that branch to then close, right? And after that, you execute else close with the opposite mask, right? And you should have a way to generate a mask. But this typically happens by comparing 2 vectors of values, right? So let's say you want to compare 2 vectors using this inequality. Then, yeah, as you can easily imagine, there's an instruction foil, but they are collectively generically called a comp instruction. So there's an instruction named comp PS, for example. Then you get the mask. So what happens is that so this instruction compares. Sorry, this should be A and B. Compares each corresponding elements of A and B, and each one is either 0 or 1, and it is returned as 16-bit mask, right? So this is actually a 16-bit integer, and this can be used for later predicated instructions. And you can change the way you compare these two vectors by specifying some appropriate symbols here. So you can check intrinsic sky the page. So yeah, okay. So let me finish this slide. Sorry, sorry for overrunning the time a little bit. So this is a typical template to vectorize loops containing branches. So let's say this loop has an if statement inside. If Ci, then it does T, and otherwise E. So the way you convert this loop looks something like this. So yeah, of course you need to get the vector of values, evaluating everything from Ci to Ci plus L minus 1. Right? So you get a mask, right? And if any bit is set, so if any then is supposed to branch to the then clause, then you need to execute this T, but with predicated on K. So you need to you want to execute this T only on lengths whose corresponding bit in K is set. And you do the opposite for the else branch. So you actually need to execute both T and E most of the time. So this is typical template. So I'm just trying to illustrate that this could be done. This can be done using instructions that are available to CPU. So it's only that the compiler cannot figure out how to. So yeah, there are a couple of other things I want to explain, but let's do it in the next week. And the next week we'll continue. So you continue working on this high-level SIMD programming exercise and sharing the results. And after that, let's dive into the manual vectorization of the code that all compilers fail to vectorize. Okay, so with that, sorry for running out of the time. So if you do not have any question, then we are done for today. Any question? Okay, so let's yeah, get it done for today. Thank you.